Welcome to lesson 5.2, use perpendicular bisectors. So last lesson we looked at mid-segment theorem and coordinate proofs. This lesson we are looking at the idea of perpendicular bisectors. So if we break down just the title before we worry about the definition here, we know perpendicular lines cross at 90 degrees or meet at 90 degrees. And a bisector means to cut something perfectly in half. So we know it will be something crossing at 90 degrees, cutting something perfectly in half. So the definition of a segment bisector is that a segment bisector intersects a segment at its midpoint. So our bisector can be a segment, a ray, or a line, or even a plane that's perpendicular to a segment at its midpoint, called a perpendicular bisector. So here, line CP is the perpendicular bisector of segment AB, meaning it crosses through AB at its midpoint P at 90 degrees. A point is equidistant from two figures if the point is the same distance from each figure. So we could say P is equidistant from A and B, because P is the same distance from A and B. But then we know any points on a perpendicular bisector, so any points on line CP here, are equidistant from A and B. So point C is also the same distance from C to A as it is C to B. And that's an important rule we want to keep in mind, because that builds into the perpendicular bisector theorem. It says, in a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So like I just said, if CP is a perpendicular bisector AB, CA is the same length as CB. And then we have the converse of that. The converse of the perpendicular bisector theorem says, in a plane, if a point, like this case, if point D is equidistant from A and B, that tells us point D must be on the perpendicular bisector of AB. So if we know DA is equal to DB, then we know D is on the perpendicular bisector of AB. So going in reverse of this theorem above. So then let's explore those theorems. Example 1 tells us line BD is the perpendicular bisector of side or segment AC. They want us to find the distance AD. So if BD is the perpendicular bisector, that tells me point D is the same distance from C and A. So I know AD here is equal to, so AD here is equal to DC here. So that shouldn't be an A, that should be a D. So fix that to be a DC. So we know AD is equal to DC because D is on the perpendicular bisector. So we can begin with finding the measure of AD by saying 5x here equals 3x plus 14, because CD here is equal to AD. So 5x equals 3x plus 14, subtract the 3x from each side, 2 times x equals 14, divide by the 2, and x equals 7. But be careful not to put the 7 as your final answer, because we know 7 is not the final answer. 7 is the value of x. We want to find the distance of AD. So we're going to put the 7 back in to the equation for AD. So 5 times 7 tells me AD's distance is 35 units. Example 2. We know line WX here is the perpendicular bisector segment YZ. What is the segment lengths in the what segment lengths in the diagram are equal? So if we know this is the bisector YZ, we know YW is equal to WZ. We also know XY, because X is the midpoint, we know XY is equal to XZ. And then by looking at the diagram, this is 25 and this is 25. So we know VY is the same distance or equal to VZ. So these three parts. So then they're asking, is V on line WX? Yes, it is. Because if V is the same distance from Y and Z, meaning 25 and 25, according to the converse of the perpendicular bisector theorem, it must be on the perpendicular bisector, in this case, line WX. And now we're going to add one additional vocab term here, which is concurrency. And what concurrency means is when three or more lines, rays, or segments intersect at the same point. So if three or more lines intersect at the same point, they're known as concurrent lines or concurrent rays or segments, depending what figure they are. The point that they meet at is called the point of concurrency. So if we look down here, P would be a point of concurrency because multiple lines meet at P. And then it says, recall that the three perpendicular bisectors of a triangle are concurrent, and the point of concurrency has a special property. So now we're going back to that idea of perpendicular bisectors. And the idea with that is concurrency of perpendicular bisectors of a triangle, theorem 5.4. It says the perpendicular bisectors of a triangle intersect at a point that is equidistant from all the vertices of the triangle. So in this case, if I have triangle ABC and I do the perpendicular bisector of each side, so the perpendicular bisector of BC, of AC, and of AB, those three perpendicular bisectors meet at a point, and that point is the same distance from my three vertices. So the distance PA equals P to B, which equals P to C, right here. So then we can use that idea to find some locations. Now for example 3, I'm going to create a short second video walking you through how to do this drawing or construction. But the main idea here is that we have 3 carts frozen yogurt, points A, B, and C outside a city. Each cart's the same distance from the distributor. They want us to find the distributor that's equidistant from the 3 carts. So our process, which I'll show you in the video, is to first connect your 3 carts to make a big triangle. And then you do the perpendicular bisector of each side. And where those 3 perpendicular bisectors meet is our distribution center. So I'll create another short video just walking you through how to draw the perpendicular bisectors. For that, you will want a protractor and a ruler. And then we can go down to example 4, which says find the value of x. Well, what we know here is this side, this is the perpendicular bisector. On this side, this is the perpendicular bisector. And on this side, there's one right here. So if I know those 3 all meet at this point, and the distance here is 12, that means the distance along this line and this red line also must be 12. So x equals 12. And that's based on our theorem right here, that that point where they meet is the same distance from each vertex. And then the final idea for today is circumcenter. And for a circumcenter, the point of concurrency of the three perpendicular bisectors is called the circumcenter. And that circumcenter is equidistant from the three vertices. So P is the center of a circle that passes through all three vertices. So acute triangles, if we did the circumcenter of an acute triangle, meaning we would do the three perpendicular bisectors, our circumcenter ends up inside the triangle. If we're dealing with a right triangle and we find the circumcenter, it ends up on the triangle. And if we have an obtuse triangle, the circumcenter is outside of the triangle. So the idea is that we could use this process here, which I'll create a video for, and when we find that circumcenter, the point where the three perpendicular bisectors meet, that can be the center of a circle that hits all three vertices of your triangle.